Hello, hi. Hi everybody, my name is Manuel Sopena and I work as a system administrator for CICS. And today I'm going to present with Hussein some of the work that we did around trying to containerize a Slurm cluster and then have it running on Kubernetes. So, as a disclaimer, this work was done in 2020, so it was some time ago. And I'm going to give a little bit of, motivation of what was behind the rationality of why we wanted to do this. So, the use case for this project was very simple. Let's say I'm a developer and I have some code I need to run on a pipeline. So my code is integrated in a pipeline, and this pipeline runs on Slurm. So what can I do in order to have replicate the Slurm infrastructure quickly to run my tests and then have feedback quickly? So then we came up with the idea of trying to do this on Kubernetes. So containerize the whole Slurm cluster and then replicate the infrastructure. This was research and development project, okay? So we never, ideally was not intended to run it on production. We wanted to understand the challenges of containerizing the different parts of an application like Slurm. The idea also was like, once we can run Slurm on containers, how can we do to make it the full idea of this cloud thing? Like all these containers should be ephemeral. You can have multiple people working on different branches, creating different commit IDs of your application, submitting all of them. How could we have a farm of ephemeral Slurm clusters to run these tests and provide feedback to the developers? We wanted to reuse technologies familiar with the center at that time, because obviously it will be easier to communicate our work to other colleagues. We also wanted to be able to run MPI, not from a performance perspective, but only just to say that we can have an MPI job running across containers. And also to have a full, how can I say, full, we just wanted to have SSH enabled. So if people want to follow up their work and then they want to connect into a machine or into a pod or a container and then be able to tweak, run their command there, their application manually or whatever, they could be able, they could access the environment through SSH.
So that was the beginning of the main idea at the beginning. At a certain point, we just moved to a second level, actually, and we tried to mimic an entire, let's say, login node on a pod, simple pod, where we have like, we were extending it to go for like Rocky 9.1 there and having modules inside it and, deploying using SPAC, different applications, so it was like really a complete, we'll show some of the snapshots there actually. That's all looking at the functionality point of view. So, but that will be coming back later to it, showing some details about it. Okay? Thank you.
We didn't care about security at that time because for us security was a burden. We wanted to focus on plugging all these different pieces together and then see how they work. We wanted to learn how to run Slurm containers on Kubernetes rather than invest much time on Kubernetes itself. Okay. So, from the containers point of view, because this is the building blocks for the whole project, we use different types of base images based on CentOS, Rocky, Red Hat based on UBI and CreateOS. The only thing here to mention is, for example, the process to create container images from Cray, because we wanted to replicate the compute nodes we have at the center. We had to, copy the root file system from a machine, modify it to add the programming environment, tweak the SSH on security things, and then export it to a container, and then to push it to a registry. For the rest was just a Docker file using the base image and then installing all the packages we needed. For example, reframe to run our tests, install Slurm, SSH, more things I will explain later. Then below you have the list of the different images we use for Slurm. SlamDBD, MariaDB for the database. One thing to mention here, as you can see, we integrated multiple services inside each image. This is, some people might think or might say, and this is an anti-pattern from containers perspective, but I will explain later why we choose going this path. So, following that, why we end up mixing so many things inside a container? Why we run Manji, why we run SSH, why we run SlamD? And this was an open question even today, if you ask many people, because this is the paradigm between system containers and application containers. When people talk about containers today, they might think one container runs one single thing, and that's it. But for us, we want to do something different. Our need was different. If we want to provide SSH, you need to SSH into the machine you want to troubleshoot the main daemon, like in this case, SlamD. So that involves having multiple daemons running inside the same container. On top of that, if we can achieve to have this, the next question will be, okay, who is going to manage all these daemons? Most commonly, people will use supervisor-D, and this is the approach we started with. But moving on, we wanted to have a fully systemd environment there. And the reason is because we thought it will be more easier. It will give us the benefit of if we want to customize the image, we just need to use cpan, install everything, and then it will add the binaries, it will add the configuration files, it will add the systemd unit files, and then basically the image will be ready to run. As opposed to superD, then you have to do all these things yourself manually. This is what I already mentioned. Now from here, the only thing is, at that time, 2020, there was a lot of uncertainty about running systemd on containers. It was not easy to find a container image which will allow to do this, but technically it was possible. Actually, if you go to that link, systemd was ready to run inside containers even before some or many of the container managements were ready to run systemd. And that link will explain to you how to make systemd understand that it's running inside a container so it can do what we intended. Today is much more easier. Many container images distributed by, for example, the one from Red Hat, they are already prepared, so not much work to do there. Now, problems or things we have to tackle configuring the different services. So for example, Manji is a very picky service because in terms of folder permissions and file permissions, and the challenge we found here is to make things simple, we thought, okay, so let's share the same Manji key across all the nodes, okay? So to do that, we just need to create a volume and then share it. But by default, the permissions on the volumes are wide open, and then Manji will complain. So one way to solve this is we just spawn an init container which will start before manji, then we'll prepare the folder permissions, and then we'll create the manji key if missing, and then eventually the manji containers will start on the right environment. Another thing is communication between Slurm and Monji. The communication is not through network per se, it goes through a Linux socket. So if you want to do that properly, then you can use just an MTD type volume. The reason I'm putting this is because we started in this way. We separated Manji with Slurm, but once we added integration with systemd, we just joined it together. So we didn't need to do this anymore. Again, it simplifies things. From here, well, just to say that for us, in our design, one pod was equivalent to one compute node. For the same reason I mentioned before, we are talking about system containers. So we will have one pod per compute node, one pod for the Slurm controller, one pod for the Slurm accounting, and another one for the login node, and so on. Then from the services, well, this is just saying, one of the tricky parts here with ephemeral containers, for example, the port SSH is not 22 anymore because you never know how many containers you're going to be running and how many SSD daemons are going to be in place. So these ports for us were created dynamically. But yeah, that's it. And this is because on our Kubernetes container at that time, it was pretty simple. It was just vanilla. We didn't have any ingress or anything like that. Then in regards to the volumes, I think I already mentioned all this. The only thing here is the Slurm configuration. It needs to be templated because the way you will spawn each cluster is through variable files where you could specify the characteristics of your containers. That you could say, I want X amount of compute nodes. I want to define the name of the cluster. I want to define the name of each compute node, the name of the login nodes. I want to share the accounting across multiple different Slurm clusters, etc. So for this case, we had to template the Slurm configuration. What else? Then the Scratch, of course, rewrite many. And that's all. Okay, and this will be like an overview of how things will look like. So if you spawn a container, you will have the freedom to put as many compute nodes as you want to put, as you want to have. Only one control at the moment, and the counting for Slurm, you could use a dedicated one for your cluster or share it across multiple ones. That depends on the person behind. And you could do that multiple times. At any point in time, you can have n number of clusters for you. Each one will be different. And yeah.
So the multi-tenancy part would go at the namespace level. So per cluster, for every namespace, you can just build a cluster there. And the only thing you need is just like try out another way of spawning this task.
No, it was pretty simple. As you said, it was through SSH. So during the configuration of the nodes, there are two types. One is to expose SSH externally. So in that way, there was another parameter where the user could say, this is my key. And then with that key, you can SSH into the pods. And then the other one is during the creation of the cluster, it will automatically generate an internal key, and then that key will be shared across all the nodes. And that's the key we'll use for MPI. We try with SSH.
I think I will cover some more because maybe there's one part that I have been working recently about, especially with testing the MPI over SSH. In this case, when you run MPI run, you should be able to communicate with all your nodes over SSH. And I have that working now. The only difference from what has been done at the early stage is that I had to start I built my completely new image where I'm firing the containers in a privilege mode, where I have like SSHD, they are just up and running without any problem, and I have like completed it for the functionality point of view. Because, security I don't care about security. I mean, someone will be screaming at me, but that will be later, let's say, and it was only really looking at the functionality point of view. And that's where we have been like looking at the, but it's a different way for starting the container itself with giving it all the privilege needed to be able to fire stuff there.
Okay, so in this case, the way we orchestrated the communication with the Kubernetes API to spawn, to configure the thing was pretty rudimentary. At that time, we just used Ansible, okay, because it will be easier for us to template the different YAML files, the SLAM configuration, and then just use the kubectl client binary to communicate with the API. And that below there is just a screenshot of how cluster will be looking. So in this case, you have 3 compute nodes, 1 accounting, 1 logging node, and 1 controller. That's it. And as you can see, each one of them has only 1 container, except the accounting one, which has 2, MariaDB and the SLAM DVD. This is just the steps that the Ansible were doing at a high level. And then, as you can see, on the last section for the sage, you have like 2 different processes. One is the internal one, which is the one used by the MPI, and the other one is just for the user to connect. This is some of the parameters of the input file, so you can specify all this, and the script will parameterize the cluster as you want. The reason why at the top you have commit ID instead of cluster ID is because behind this, or working next to it, there was a CI/CD pipeline. So basically I have my code, I commit, and when I do push, that commit ID will be the identifier for the cluster. So then I know if there are multiple clusters at the same time, I know by the commit ID which is the one with the changes I introduced. So then it will be easier to identify who belongs to what from the user's, developer's perspective. And that's it. The rest is pretty much self-explanatory. And here are more screenshots. So top one you can see is just running PSaux just to see that the SLAM systemd is running and all the daemons are brought up and running. Like you can see SSD, you can see manji, SLAMD, and then the dbus from systemd. And below is just a test of an MPI job with all the ranks for the different compute nodes.
So what I would like here to everything has been introduced, and since the beginning, I thought for a period of time that we could go beyond what was the main idea. I mean, is this container part, is it like a real solution for loading a real HPC workload? I mean, would Kubernetes be like a service that offers a real HPC workload? That was one question came to my mind, and that's why I wanted to bring it to the edge. So to go to the maximum part where I can really run as if I am running on a bare metal machine. Now, regardless of the resources. And I started by trying to, when I'm compiling stuff, I would like to run over Slurm and using PMIX. And I can, here you raised up first earlier, you raised about PMIX, and I did not manage to get it working. It was giving some kind of errors that was not super clear for me. I opened the case with OpenMPI, but I never get an answer about it. But anyway, I managed then to get it working with PMI2. And that worked. with some environment variable. And now the next step was just, okay, now we have it functional. I have like some MPI job running using using Slurm in a way that I'm expecting in a real-based bare metal machine. Now I would like to run some more serious application or start measuring to see how I can do it from the network point of view and how I can do things. And there it was like the easiest thing, let's get Ozu and just start running some network part. And there it was not an easy process because, you know, Kubernetes itself, you have to go to a different level. So you have the bare metal network and then you have Kubernetes network and then it's going to jump from one to another. And it's a bit tricky because, you know, if you run the first job, you start running some bandwidth or latency, you'll see some runs will just go perfectly fine and you have good latency, while then you run it again and you see that will be just like go like 4 or 5 times. And the reason simple, then you just find this stuff because the pods where they are running, if you look at of the nodes, and then you can see there's like this NID 003207, and you can see there are like 3 pods that are running on NID 3207. Is this 3? Yeah. And then you have like the rest are running in 6 and 5. So just running the latency and the bandwidth tests on the pods that they're running in node 7, so they are not going over the network. It's like running an application, running multiple applications on your laptop, so it's going to be using the loopback. And that's where you start seeing like, you know, interesting numbers. Well, when you are running from one pod on 7 and one pod on 6, that you will see that's what expected to see from a bandwidth and latency. Now, the issue there was raised is that, okay, now what I'm going to do, I'm going to try to use the Rocky or RDMA over, in this case, in our case here, libfabric. And there I had like some difficulties. And at the beginning, I thought was the problem is the Kubernetes itself. And then Christian gave a hint and told me, like, try to do that over the container itself. I mean, instead of going over Kubernetes. And I was able to produce the same number, exactly the same results. So it was the Docker itself. So it's not Kubernetes, which not allow me to do that. It's just Docker. And then later we're just looking at it and could be like, we found out that the issue could be like the MAC address itself, because the MAC address has a weird format that's not accepted from the interface. But that's a different discussion. So that's where we did not see, and let's say from a performance point of view, the expected number that I'm getting in the host. I'm getting in the host like full bandwidth space on the interface, but in the container itself, I was not getting these numbers because still some more to work. So functionality, we have it. We have functionality and we are running. So imagine here we can run whatever application on one of these compute nodes. So what happens when you're running a job, it will become like a process inside the container. And you have like 16 process, you'll see 16 process inside this container, and that could scale up the way that you want. As much resources, because we limit some resources here in every container. And also we have seen a drop because from a software point of view, you know, container, when you're running it, even if you have like 400 gigabit interface on the host, you will see only 10 gigabits. So the container itself will just create an interface with 10 gigabit per second instead of whatever the host it has. Now, we have been trying to do the privilege or whatever privilege allowed to us, but still some more. So functionality, we have it. We have, I can show you that we have also modules there are running. We have, and this is a version of Rocky that we are using. We have been using some scientific application. We managed to get that compiled and working, but definitely we are not talking about performance we're expecting. So definitely you can get like a complete scientific application there. And whatever you need to map to the container, you can do that. Back to what has been presented earlier, that between these different versions of container, I think Do It Now, they presented these 4 versions of container that we're talking about, mentioning about which one is real HPC and which one is not. And I think we start seeing like similar results from Docker itself. I mean, that's where there are a lot of work to be done, which is on top of it that pays a penalty Kubernetes, but we have to look at what's runtime engine behind. Okay. I think I'll see here just like showing this SSD that's running, and this is getting up and running actually on when I'm firing. So I don't have to start the daemon. It's already enabled there, and I don't have to do anything more than that. I think that's more or less I covered, I believe, part of this future work. So I talked about functionality, security, I don't care. Performance is just something important. I mean, definitely security here. I can see the security manager just raising his hand. Well, that's not true that I don't care. I definitely care because we are running the container in the privilege mode, and that's not, I believe that's not the correct approach for production. But at least to prove this concept was very important to remove any obstacles. And then next step, we'll see how we can do it. Yes, performance, as soon as we'll get this, or the main part is run, I think we're going to repeat all these steps we did, and I'm expecting that at least we should be able to hit, not sustain this 10 gigabit, but at least we should be able to be close to it from a bandwidth point of view. Hopefully from latency, we'll see what we can do based on that. I don't know if you want to add anything there. You have like some more affinity. Yeah.
Okay. So I don't know if anyone has any question.
Which network CSI you used for this proof of concept? Flannel?
CNI, we have the different possibility to use different CNI actually, and on this system we're using Calico. Calico is a CNI, and Cilium could be used there also. So behind the deployment of Kubernetes, it goes through from rancher management, actually. And this is really in a short time to bring everything up and running. I can tell you like 15 minutes, you get Kubernetes up and running. And I'm talking about really, new nodes are deployed. And to get the Slurm part is like about 3-4 minutes. So you have your Kubernetes and Slurm up and running in like 20 minutes at maximum time.
Any last questions? Okay.
Thank you.
Thank you, Hussein and Manuel.
Thank you.
Bum,